Yesterday we discussed two-dimensional close packing, how the constituent particles are packed in the crystal. One dimension means there is only one way in which the spheres are arranged in one-dimensional close packing structure. In this arrangement, each sphere is touching two neighboring spheres. Hence, in this arrangement, the coordination number is 2. And this is the two-dimensional close packing structure. And here, when the rows are stacked over each other, a two-dimensional closed packed structure is produced. This stacking can be done in two ways. One is square close packing, another is hexagonal close packing. The first one, the spheres in the second row may be placed in such a way that they are touching the spheres of the first row and are exactly above the spheres of the first row. That means there is horizontal as well as vertical alignment of the spheres in the two rows. If the first row is called A, then the second row being exactly the same will be also A type. Further, the rows may also be built up exactly in the same manner. Hence, we call this arrangement as AA type. And in this arrangement, each sphere is touching with 4 other spheres. Hence, the coordination number is 4. On joining the centers of the 4 spheres touching the particular sphere, a square is formed. That's why it is called square close packing in 2 dimensions. And the spheres in the second row may be placed in the depression of the first row. This produces a row different from the first row. First row you call it as A, the second row you may be called as B type. When the spheres in the third row are placed in the depressions of the second row, then the third row is exactly similar to the first row. And third row is called A type. And fourth row is vertically aligned with the second row. Hence, the coordination number here is 6. How it is 6? You can see the diagram. And each sphere is touching 6 other spheres. So, this arrangement we call it as two-dimensional hexagonal close packing. I hope you understood this two-dimensional close packing in solids. Now, coming to the three-dimensional packing. Three-dimensional close packing from two-dimensional square close packing. Two types are there here. One is 3D close packing from 2D square close packing. Another one is three-dimensional close packing from the two-dimensional hexagonal close packing. Because two-dimensional close packing, two types are there, square close packing and hexagonal close packing. And from that we get a three-dimensional close packing. First we discuss three-dimensional close packing from two-dimensional square close packing layers. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally as well as vertically. Similarly, we may place more layers one above the other. If the arrangement of the spheres in the first layer is called A, all the layers have the same arrangement. Thus, the lattice has the type A pattern. The lattice thus generated is the simple cubic lattice and its unit cell is the primitive cubic unit cell. And here you can see the structure, three-dimensional close packing, and this is the first layer, second layer also there. It is similar to the first layer. It is arranged three-dimensionally and it is generated and you get a structure like this. Now placing the second layer over the first layer. First layer is there, just imagine. And now second layer we are going to place above the first layer. In the first layer you could see the voids. Voids means gap. You can see the voids, triangular shaped voids everywhere. And here it is mentioned, above also it is there, below also it is there. So everywhere, the voids are there. Wherever a sphere of the second layer is above the void of the first layer, a tetrahedral void is formed. Here you can see above this another second layer here, dotted line you can see nicely. So three spheres are there. Now here one void is formed. Above that one layer is there. So total that void is surrounded by 3 plus 1. Total 4 spheres are there. So a tetrahedron is formed when the centers of these 4 spheres are joined, and they have been marked as T here. You can see nicely. Now I am going to draw and show you how tetrahedral void is formed. Now you see this is the first layer, just I am drawing. This is the first layer, first row I am drawing, and first layer I am drawing. Second row occupies the depression in the first row. Again third row occupies the depression in the second row. Like this it is arranged. Now you can see the voids here. This is the void. The gap, formed here. Everywhere the gap is formed. Like this. And now this is the first layer. Suppose this layer you take it as A. Now the second layer I am drawing. You see. This is the second layer. Now you see the void. Now it is touching how many spheres, 1 above and 3 below. So total how many spheres are there around that particular void? You see how many? Total 4 spheres. So each void is surrounded by the 4 spheres. That void we call it as tetrahedral void. At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these don't overlap. One of them has the apex of the triangle pointing upwards and the other downwards. And these voids have been marked as octahedral void. Such voids are surrounded by 6 spheres and are called octahedral void. And the number of these two types of voids depend upon the number of close packed structure. Any close packed structure, if you see, n number of spheres are there. In that, the octahedral voids generated is n. N spheres are there. 10 spheres are there means 10 octahedral voids will be there. But the tetrahedral voids will be just double, 2n. Suppose 5 spheres are there, then 5 octahedral void will be there and 10 tetrahedral void will be there. Now I am going to show you what is octahedral void. Now I am keeping the first layer. Second row I am keeping with the help of bangles. You can understand each bangle is a sphere. Just I am keeping. This is first row. This is second row. First layer I am keeping. Right? Now triangular shape voids are formed. You could see nicely the voids here. Now the second layer I am keeping, covering that void. Second layer I am keeping. You see now second layer I kept. In the second layer you can see nicely one void is formed here. Can you see the void here? Here one void. It is, this void is surrounded by how many spheres? Here one bangle is there and down 3 bangles are there. So total 4 spheres touching that void. So the void formed by 4 spheres is called tetrahedral void. Now you can see nicely here one void is formed. Can you see the void formed here? Here one void is there. You can see nicely. I will show now the void formed. See here it is a one void and here one void. This void is tetrahedral void. Now you see this void, it is surrounded by 3 spheres of top and bottom 3 spheres are there. Total 6 spheres are there. So this void is formed by 6 spheres. This void is touching 6 pairs. 6 pairs forming this void. This void we call it as octahedral void. This is tetrahedral void. This is octahedral void. This is also octahedral void. This is tetrahedral void. So this is octahedral void. Octahedral void means 3 plus 3 total 6 spheres form that octahedral void. And 4 spheres means it is tetrahedral void. Now the third layer I am covering the tetrahedral void. If I cover this tetrahedral void, the third layer, suppose I cover octahedral void first. I am covering, then totally new layer arrangement will be there. First layer you take it as A, second layer you take it as B, third layer it is C. And this arrangement we call it as ABC type. That means fourth layer will be vertically aligned with the first layer. A layers are different, B layer different and C layer different. Fourth layer is vertically aligned with the first layer. Suppose I cover the tetrahedral void. This tetrahedral void, where tetrahedral void? Everywhere, this is the tetrahedral void. I am covering that tetrahedral void. Then it will be vertically aligned with the first layer. See, if I cover the tetrahedral void, then third layer will be vertically aligned with the first layer. That arrangement we call it as AB type. So here two voids are formed. You understood what is tetrahedral void and what is octahedral void. Now the third layer, if it covers the tetrahedral void, then the type it is AB type. If the third layer covers the octahedral void, then we get to the close packing arrangement ABC. This is octahedral void and this is tetrahedral void. Tetrahedral void 4 spheres. Octahedral void 6 spheres are there. This is octahedral and this is tetrahedral. Third layer covers the tetrahedral void. The type is AB type. If the third layer fully covers this octahedral void, then the type what we get is ABC. And I told already 3-dimensional close packing, and two types of voids are there, tetrahedral void and octahedral void. Tetrahedral void, if the third layer covers the tetrahedral void, the type is AB type. It is called hexagonal close packing. And if the third layer covers the octahedral void, then the close packing what we get is cubic close packing. So 3-dimensional close packing, one is hexagonal, another is cubic close packing. From hexagonal close packing of 2-dimensional close packing. I discussed already. In both HCP and CCP, the methods of staking, a sphere is in contact with 6 other spheres in its own layers. It directly touches 3 spheres in the layer above and 3 spheres in the layer below. The sphere has 12 close neighbors. Number of nearest neighbors in a packing arrangement is called coordination number. So in close packing arrangement, whether you take a hexagonal close packing or cubic close packing, each sphere has the coordination number of 12. So what is coordination number? The number of nearest neighbors in the close packing arrangement is called coordination number in solids. And placing the third layer over the second layer, I explained already. Covering the tetrahedral void, the third layer covers the tetrahedral void. When the third layer is placed over the second, there are two possibilities. One is covering tetrahedral void, another possibility is covering octahedral void. Covering tetrahedral void, the tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This pattern is often written as AB pattern, and this structure is called hexagonal close packing structure. This sort of arrangement of atoms is found in many metals like magnesium, zinc, etc. So I hope you understood this covering of tetrahedral void. First layer will be there, and first layer, second layer, when you keep the second layer, two types of voids, tetrahedral voids and octahedral voids formed. If the third layer covers the tetrahedral void, then the pattern what we get is AB type. And here it is shown clearly. This is your first layer. Now B is your second layer, and the third layer covers the tetrahedral void, then the third layer will be exactly vertically aligned with the first layer. That's why A is repeated again here. Then B. That means the fourth layer is vertically aligned with the second layer. This pattern we call it as AB pattern. It is nothing but hexagonal close packing. It is hexagonal in shape. This is first layer. This is second layer. Third layer is vertically aligned with the first layer. So A, B, again A is coming, then B. So this is hexagonal close packing. 3D hexagonal close packing. Now coming to the third layer covering octahedral void. The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral void. Then when placed in this manner, the spheres of the third layer are not aligned with those of either of the first or the second. This arrangement is C-type. Say first layer is there, second layer is there. Now the octahedral voids formed is covered by the third layer, then it is not vertically aligned with the first layer. New layer is formed, that is C. So A is there, B is there. After that A is not coming, C is coming. And then fourth layer will be vertically aligned with the first layer. That's why this type of arrangement we call it as ABC pattern. Only when fourth layer is placed, its spheres are aligned with those of the first layer. This pattern of layers is often written as ABC, and it is called cubic close packed or face-centered cubic structure. The example, the metals such as copper, silver crystallize in this structure. I hope you understood this. Three-dimensional close packing from two-dimensional close packing, square close packing and hexagonal close packing. Square close packing of two dimension gives only AA type, and hexagonal close packing of two-dimensional structure gives two structures. One is HCP, another is CCP. Just I will show. Two-dimensional close packing, two are there. One is square close packing, another is hexagonal close packing. Square close packing, two dimension, again it is arranged in a three-dimensional way and forming AA type, that is primitive cubic system you get. And a hexagonal close packing 2D gives the 3D alignment, two possibilities. One is HCP, another is CCP. HCP means hexagonal close packing. CCP means cubic close packing. This is AB type. This is ABC type. Next we discuss packing efficiency in a simple cubic unit cell. What do you mean by packing efficiency? Packing efficiency is nothing but the ratio between volume occupied by all the spheres in unit cell and the total volume of the unit cell. Percentage means you have to multiply by 100. So volume occupied by all the spheres in the unit cell divided by total volume of the unit cell into 100. Suppose you take this is a simple cube. It is drawn here. Simple cube means only the corners are occupied. And let A be the edge length of this unit cell and R be the radius of the sphere, and the spheres are touching each other, and therefore A edge length is equal to 2 into R. R is radius. Number of spheres per unit cell in the case of simple cube we discussed already. In the case of simple cube, only corners are occupied and each corner is shared by 8 unit cells. So only 1/8 portion will be there in each corner. So 1 by 8 into 8, 1. So number of atoms per unit cell in the case of simple cubic system is 1. And volume of the sphere, the formula you know very well, 4 by 3 pi r cube. So volume of the cube is A cube, that is edge length cube, that is 2r cube, that is 8r cube. So the packing efficiency will be 1 by 3 pi r cube divided by 8r cube, that is nothing but 0.524. And percentage means you have to multiply by 100, that is 52.4 percentage. I hope you understood this. So packing efficiency in the case of simple cubic unit cell is 52.4%. The rest are empty spaces. Only 52.4% only occupied by the spheres in a simple cube. Next, going to the body-centered cubic structure. Here one cube is drawn and the corners, corners of this cube, it is mentioned as this corner A, B, C, D, E, F, G, H, and the spheres occupies the corner as well as the one sphere will be there in the center of the body. So center of the body also occupied by the sphere. And in the body centered cubic unit cell, if you take a triangle AFD, what is AFD? A, F and D. A, F and D. AFD, and let AD is taken as the A, the edge length, and DF is that length, we call it as what? B. And B square, you apply your Pythagoras theory here. B square is equal to A square plus A square, that is equal to 2A square. And AFD, this is taken, and this is A square and this is B square. So here, and AF, this is C. So C we have to calculate. So B square is equal to A square plus A square, that is 2A square. And let AF is equal to C. So, and we know that FD is B and AD is A. So C square is equal to A square plus B square. And what is B square? B square, and B square, it is calculated from this two. Actually first you have to take the triangle. This triangle you have to take. And in the triangle, this is A, and this is B. So B square is equal to A square plus A square, that is 2A square. This they calculated B square. Now they have taken this triangle now, AFD. In that, B square is nothing but 2A square and A square. So C square they are calculating. So C square is equal to A square plus B square, that is equal to A square plus 2A square, or C is equal to root 3A. And we know that C is body diagonal. As the sphere at the center touches the sphere at the corner, therefore body diagonal is equal to, that is C is equal to 4R, or root 3A is equal to 4R. So finally A cube is equal to 4R divided by root 3 the whole cube. So when you substitute this in the packing efficiency formula, the total volume of the sphere of the unit cell divided by, the volume occupied by the spheres divided by the total volume of the unit cell into 100, if you apply, then what you get will be finally 2 into 4 by 3 pi r cube, that is the total volume occupied by the spheres. 2 into 4 by 3 pi r cube, volume occupied by the two spheres in the unit cell, divided by the total volume of the unit cell is nothing but 4 divided by root 3 or the whole cube. Finally what you get is 68%. Calculation of packing efficiency of BCC. Structure 1 BCC I have drawn here, and corners taken as A, B, C, D, E, F, G and H. And here body diagonal, it is taken as C, and this face diagonal, it is FD, it is taken as B, and this distance is taken as A, and this A and this A. As the sphere at the body center touches at the corners, the body diagonal, this is body diagonal, AF is nothing but 4R. This is 4R. Why? Because here 1R and here 1R, here 1R, here 1R. And face diagonal, square root of FD square is equal to FD square is equal to ED square plus EF square, square root of EF square plus ED square, that is equal to ED is A. So A square plus A square, that is root 2A is nothing but FD. And body diagonal AF, this is taken AF, and AF is equal to square root of FD square plus AD square, and FD square it is taken as 2A square, and AD square it is taken as A square. So that is nothing but root 3A. And finally 4R is equal to, for AF is nothing but 4R. So 4R is equal to root 3A. A is equal to 4R divided by root 3. And A cube is nothing but volume of the spheres. A cube is equal to 4R divided by root 3 the whole cube. And the volume of the two spheres, BCC means 2 atoms per unit cell. So 2 into 4 by 3 pi r cube, that is 8 by 3 pi r cube divided by A cube. What is A cube here? So packing efficiency can be calculated. It is nothing but the total volume of the unit cell divided by the volume occupied by the spheres into 100. The volume occupied by the spheres is 4r divided by root 3 cube, and total volume of the unit cell is nothing but 2 into 4 by 3 pi r cube into 100 gives you 68%. Next, packing efficiency in FCC, that is a cubic close packing. I have drawn the cube and corners are occupied, as well as the face, center of the face also occupied by the sphere. So total 6 faces are there, and corners it is indicated as A, B and C, D, E, F, G, H. And here center of the face one sphere is there and corners also occupied by the spheres. Now as the spheres on the face center is touching the sphere at the corners, now you take AC, this AC, it is taken as B, this is nothing but 4R, and AC is equal to, how will you calculate using Pythagoras theory, the triangle ADC. I am taking the triangle ADC, and this distance taken as A and this distance taken as A. So AC is equal to AD, square root of AD square plus DC square, that is square root of A square plus A square, square root of 2A square, that is root 2A. AC is root 2A. And what is AC? It is 4R. So 4R is equal to root 2A. So A is equal to 4R divided by root 2. And what is A cube? You have to cube it. That is nothing but volume of the unit cell. And here packing efficiency, volume of this volume occupied by the spheres in the unit cell. So packing efficiency is nothing but, in the FCC 4 atoms per unit cell, so 4 into 4 by 3 pi r cube, this is the total volume of the unit cell divided by the volume occupied by the spheres, that is nothing but A cube, into 100 gives you 74%. In a crystalline solid, there is a regular arrangement of constant particles. However, this arrangement is generally not found to be perfect. This is because a solid contains a large number of small crystals, and some of these crystals may not have a perfect regular arrangement of the constraint particles. This happens when crystallization takes place at fast or moderate rate, because the constraint particles may not get sufficient time to arrange themselves in a perfect order. Even if we prepare the single crystals by carrying out our crystallization experiment at extremely slow rate, the single crystals may not have a perfect arrangement. That means none of the crystal has a perfect arrangement of constraint particles. So any departure from the perfectly ordered arrangement of constraint particles in crystal is called imperfection or defect. And the defect may also arise due to heat absorbed by the crystals from the surroundings, or maybe due to the presence of impurities in the crystal. So there are of two types of defects we could see. One is point defect, another is line defect. And when the deviations or irregularities exist from the ideal arrangement around a particular point or an atom in the crystalline substance, this defect we call it as point defect. However, when the deviation from the ideal arrangement exists in the entire row of the lattice points, then the defect is called line defect. So point defect we have to concentrate here. And defects in solids, the point defects, there are of three types. One is impurity defect, another is stoichiometric defect, third one is non-stoichiometric defect. All the three are point defects. We will discuss one by one. Now stoichiometric defect, if imperfection in the crystal are such that the ratio between the cations and anions remains the same as represented by their molecular formulae, is called stoichiometric defect. And these stoichiometric defects are also called intrinsic defect or thermodynamic defect. Again, the stoichiometric defect is classified into vacancy defect, interstitial defect, Schottky defect and Frankel defect. And non-stoichiometric defects are classified into two types, metal excess defect and metal deficient defect. We will see one by one. Now you take imperfection are defects in solids. The point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in the crystalline substance, whereas the line defects are the irregularities or deviations from the ideal arrangement in entire rows of a lattice point. These irregularities are called crystal defects or line defect. Now coming to the point defect, I told already point defects, they are classified into vacancy defect, interstitial defect, Schottky defect and Frankel defect. Stoichiometric defect, these are the point defects that don't disturb the geometry, Types of point defects. Number 1, stoichiometric defect. These are the point defects that don't disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are of two types. One is vacancy defect, another is interstitial defect. Vacancy defect, when some of the lattice sites are vacant, from the word you can understand, some of the lattice sites are vacant, the crystal is said to have a vacancy defect. This results in decrease in density of the substance. This defect can also develop when a substance crystal is heated. Second type is interstitial defect. When some constrained particles occupy an interstitial site, the crystal is said to have interstitial defect. This defect increases the density of the substance. So 2 points you have to highlight here. Vacancy defect means density decreases. Interstitial defect means density increases. And vacancy and interstitial defects, as explained above, can be shown by non-ionic solids. And ionic solids must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, they show these defects as Frankel and Schottky defects. Vacancy defect means here the arrangement of cation and anion, it is taken A plus B minus like this, and one place it is vacant, but it occupies the interstitial site, but this place is vacant. An interstitial defect, regular arrangement is there and even interstices also occupied by the atoms. Next is Frankel defect. Frankel defect means it is shown by ionic solids. It is also coming under stoichiometric defect only. The smaller ion, that is usually cation, you know very well, cation is smaller than anion. Smaller ion is dislocated from its normal site to an interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. And here vacancy defect is also there and interstitial defect is also there. And Frankel defect is also called dislocation defect, but it does not change the density of the solid. It is shown by ionic substances in which there is a large difference in the size of ions. For example, zinc sulfide, silver chloride, silver bromide, silver iodide. Due to the small size of zinc 2 plus and Ag plus ions, that means the cations and anion size difference is larger. In these cases only you could see this Frankel defect. And here Frankel defect is shown here. And one ion is moving from its site. Here vacancy is created and it occupies the site other than its original site and it occupies the interstitial site. Dislocation occurs. Next is Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain the electrical neutrality, the number of missing cations and anions are equal. Like simple vacancy defect, Schottky defect also decreases the density of the substance. And number of such defects in ionic solids is quite significant. For example, in NaCl, there are approximately 106 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube, there are about 1022 ions. Thus, there is one Schottky defect per 1016 ions. Schottky defect is shown by the ionic substances in which the cation and anion are of almost similar sizes. Frankel defect means cations anions size difference is larger. But here cation and anion are almost similar in size. For example, NaCl, KCl, CaCl, silver bromide. It may be noted that silver bromide shows both Schottky as well as Frankel defect. Diagram, and here you see one anion is missing and one cation is also missing, and here one anion is missing, one cation is missing. So equal number of anions as well as cations are missing from their lattice site. That defect we call it as Schottky defect. Next type is impurity defect. If molten NaCl containing a little amount of SrCl2 is crystallized, some of the sites of Na plus ions are occupied by Sr2 plus. So each Sr2 plus replaces 2 Na plus, because charge Na means plus, Na plus only, but Sr2 plus. So 2 Na plus are replaced by 1 Sr2 plus. It occupies the site of one ion and the other site remains vacant. And the cationic vacancies thus produced are equal in number to that of Sr2 plus. 2 Sr2 plus are there, 2 vacancies will be there. Another simpler example is the solid solution of Cd cadmium chloride and silver chloride. Here 2 Ag plus is replaced by 1 Cd2 plus. Here you see vacancy defect and interstitial impurity. One impurity is introduced. Schottky defect and Frankel defect, difference between them I tabulated here. Schottky defect due to the equal number of cations and anions missing from the lattice sites, and Frankel defect is due to the missing of ions from the lattice sites, and these occupy the interstitial site. And Schottky defect, the decrease in the density of the crystal. Frankel defect, it has no effect on the density of the crystal. And Schottky defect is found in highly ionic compounds with a high coordination number and having anions and cations of similar sizes. Example, NaCl and cesium chloride. But Frankel defect is found in crystals with low coordination number and in which the difference in the size of cations and anions is very large. Example, silver halides. Non-stoichiometric defects. If as a result of imperfections in the crystal, the ratio of the cations to the anions becomes different from that indicated by the ideal chemical formula, the defects are called non-stoichiometric defects. And these defects result in either excess of the metal atoms or excess of non-metal atoms or deficiency of the metal atoms. First we discuss metal excess defect. When will be the metal excess? One is by anionic vacancies. Second one is by the presence of extra cations in the interstitial sites. When the metal will be excess? By anionic vacancies. By anionic vacancies. So metal excess due to anionic vacancies when alkali metal halides like sodium chloride and potassium chloride shows this type of defect. When they are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal and Cl minus ions diffuse to the surface of the crystal and combine with Na atoms to give NaCl. This happens by the loss of electron by the sodium atoms to form Na plus ions. Now the released electrons diffuse into the crystal and occupy the anionic sites. As a result, the crystal now has an excess of sodium. The anionic sites are occupied by the unpaired electrons are called F centers. They impart yellow color to the crystals of NaCl. The color results by the excitation of these electrons when they absorb energy from the visible light falling on the crystals. Similarly, excess of lithium makes LiCl crystals pink and excess of potassium makes potassium chloride crystals violet. You can remember easily KCl violet, Kv you can remember, and LiCl it gives a pink color, that is lip. You can remember easily. So first one is anionic vacancies and what are F centers? Very important question. A negative ion may be missing from its lattice site leaving a hole which is occupied by an electron, thereby maintaining the electrical balance, and the sites containing the electrons thus trapped in the anionic vacancies are called F centers, and they are only responsible for imparting color to the crystal. F means Farbe. Farbe means German word color. So NaCl heated with Na, you get yellow color. LaCl heated with lithium, you get pink color. Excess of potassium in KCl gives violet color. And this defect is similar to Schottky defect, and it is also found in crystals having Schottky defect. I hope you understood this. Second is metal excess due to the presence of extra cations at the interstitial site. When zinc oxide is white in color at room temperature, but on heating it loses oxygen and turns yellow. Very important question. Why zinc oxide is yellow in hot and white in cold? So whenever zinc oxide is heated, it gives Zn2 plus half O2 plus 2 electron. Now there is excess of zinc in the crystal and oxygen is liberated. Now its formula becomes is zinc 1 plus X or O1, and the excess Zn2 plus move to the interstitial site and the electrons to the neighboring interstitial site, and here also metal excess occurs. Next is metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A typical example of this type is iron oxide, which is mostly found in the composition of Fe 0.950. It is not exactly 1:1 ratio, it is 0.951 oxygen 1. It may actually range from 0.93 to 0.96. In crystals of FeO, some Fe2 plus cations are missing, and loss of positive charge is made up by the presence of required number of Fe3 plus. That means 3 Fe2 plus are replaced by 2 Fe3 plus. And F center diagram is given, you can see.